So let's look at some historical experiments that are of particular significance. J.J. Thomson, 1856 to 1940, constructed what's called a cathode ray tube. It's a partially evacuated glass tube. So here we have a diagram showing that, and here's an actual photograph of one. So there's a glass tube. It's partially evacuated. There's a little bit of gas in here, but not as much as there would be like in the air. And then you apply a high voltage across this. So in a sense, it's a little bit like a fluorescent lamp, but not exactly. So here's the cathode. That's the negatively charged electrode. And we have a positively charged electrode on this side. There's no wire connecting those, but the voltage will generate cathode rays that will flow from the cathode to the anode. And here in this picture, you can see that cathode ray. So it's a beam of particles going from the cathode to the anode. There has to be some current. In order for current to flow, some particles have to move, and that's the cathode ray. So he studied this cathode ray, and he found that those particles have these properties. They travel in straight lines. They are independent of the composition of the material from which they originate. You can make that cathode out of different metals, but the cathode ray is always the same. And he also found that they have a negative electrical charge. So electrical charge is a fundamental property of some particles. And it results in attractive forces and repulsive forces, much like magnets do, but it's an electric field instead of a magnetic field. So what we need to know about electrical charge is that opposite charges attract, just like opposite poles of magnets attract. And like charges repel each other. So, my kids used to play with Brio trains, and they connect with little magnets. And they just click together, and then you can pull them all over the place. If you take one of those cars and you turn it around, you've changed the polarity. Now you've got maybe a north pole going on. And you can try to push them together, but they'll just spring apart because the magnets repel each other. That's the same thing that happens with like charges. And then if we take charges that have the same magnitude here, this one has a +1 charge and this one has a -1 charge, we put those together, their charges add up to 0, and overall the combination has no charge. But if you pull them apart, they each still have their own charge. Any questions about that? So Thomson made a different looking cathode ray tube with this big end on it, and he's looking at deflecting these particles using electric fields and using magnetic fields. So here's the cathode and the anode, and the charge that's generating the cathode ray. The anode has a little hole in it, and that allows the cathode rays to go zinging through. And the undeflected beam will go straight because these particles travel in straight lines. But the particles have negative charges, so you can apply an electric field here and bend the particles. And so depending on how the field is applied, you can make them go up, you can make them go down. And he also has a magnetic field here, and he can adjust the magnetic field and move them that way as well. And from looking at this information, he was able to arrive at a charge to mass ratio. He couldn't measure the charge or the mass separately, but he could get the ratio from this experiment. So he found it was minus 1.76 times 10 to the 8th coulombs per gram. So coulomb is a unit of charge, and that's all we need to know about it. Based on the knowledge of charge, this implied that the cathode ray particle was about 2,000 times lighter than the smallest known atom. And this is a bit mind-blowing because they thought atoms were the smallest particles there were. And hydrogen's the smallest atom, and so nothing could be smaller than hydrogen. And yet here is something smaller than hydrogen. The indestructible atom could be chipped away. You could chip electrons off of it. Craziness. He had discovered the electron. That cathode ray is a stream of electrons. And that's why some electric current will flow through there, is because electrons are moving through this partially evacuated tube from one electrode to the other. This electron is present in all elements. So atoms of different elements are different from each other, but they all have this same particle inside of them that's the same. So that was a big deal. Finally, we get to an American physicist, Robert Millikan, did a famous experiment in 1909. Well, it's famous now. It's called his oil drop experiment. From this experiment, he was able to figure out the charge on a single electron. So, I forgot the guy's name. Thomson. Thomson found the charge to mass ratio. Millikan found the actual charge of a single electron, and from that and the charge to mass ratio, he was also able to find the mass of a single electron. Okay, so here's an illustration of his setup. He's at this big chamber, an atomizer up here, not unlike a perfume atomizer, but he's atomizing oil. And so it makes this very fine mist of oil droplets. And of course, they are subject to gravity and they will fall. He's got a big plate here, so they can't just fall all the way to the bottom, but there is a small hole here. So some of those particles will fall through the hole in this floor, basically. And they will keep falling until they get all the way to the bottom. But this plate has a positive charge on it, and this has a negative charge on it, and that can be adjusted. We have a light source here so we can see what's going on in there, because these particles, oil particles, little droplets, are big enough to see with this microscope. So we can watch the particles falling. That's all fun and everything. But what's really important is we put some ionizing radiation in here and hit those particles. That gives them a charge. If they have a charge on them, they're going to get a negative charge from that ionizing radiation. Now they're going to be attracted to the positive plate and repelled by the negative plate. And so if you adjust that just right, you can get that little oil droplet with a charge on it to suspend in the air. Pretty cool. So let's watch this video about that.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhere to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28 grams, is an exceedingly small mass.
So I'm showing you this not because I want you to be able to do those calculations, but I want to give you a glimpse into how scientists figure this stuff out. Because how do you study something that's way too small to see? Electrons are too small even for a scanning tunneling microscope. We don't have any images of electrons. And this is back in 1909 when electricity was a novel thing, right? Indoor plumbing was really, really cool back in 1909. So one of the fun things about science is it is a lot of problem solving, puzzle solving or solving riddles. How can I figure out this information about this thing I can't see? And so people come up with very creative solutions for that. Any questions about that experiment? So he could figure out the mass of the drops because he could watch how fall they fell. Oh my goodness. How fast they fell. And how fast those drops fall is determined by the acceleration due to gravity and the mass of the drops. And then he could measure the strength of the electric field required to stop them from falling. And he could get the charge on the drops. Now the drops were different sizes. The charges especially were different sizes. So what he did is he looked at all these different charges and he found that they all had one common factor. They were a whole number multiple of this crazy looking number, negative 1.96 times 10 to the minus 19. And so that had to be the charge of a single electron. Some of those droplets might have had 3 extra electrons on them, or 7 or something, but they were all a whole number multiple of that charge. And using this information and the charge to mass ratio that Thomson had gotten, then he could get the mass of an individual electron, which is like crazy small. It's way smaller than an atom itself.